There we go. We are recording. And take it away, Trevor.
Alright, so like you said, feel free to ask questions whenever you want. This is going to be kind of a more of a low-key thing with the small number we got here, so if you want to chime in if anything doesn't make sense, feel free to stop me at any point and ask questions. So, what we're going to talk about today is designing a Flappy Bird game using Pygame, and then we're going to have an application called Neat, and it's going to go ahead and play the game for us. So Neat is a neuroevolution of augmenting topologies. So you're going to hear me call it Neat instead. And it's an evolutionary or genetic algorithm for creating artificial neural networks. So if you want to learn specifically how it works, I'm going to cover some basics of it, but it's much more complicated than what I can cover in the scope of this. So I would highly recommend reading the documentation for it, or one of Kenneth O'Stanley's papers. He's the creator of it. He has some very low level and some very high level papers. There's one in particular that I would recommend that I'll link here in a little while. And it's about 6 pages long, and if you read it once or twice, you'll understand pretty much everything you need to know for it. So some of the requirements that you'd need to run it is Pygame and Neat Python. So if you have Python installed, you literally just go to the command line. And for me, my pip actually isn't recognized, so I have to type in a flag to actually get it to run. And then you just install just Pygame or Neat Python. So Neat, not Python, is a completely different library and it will not get you what you want. But if you just run that, it'll just install it for you and you're ready to go. So because this is going to be object oriented, we basically start by what do we want, what is going to be a class for an object, and what's not going to be. So ideally, you want the classes that are going to be helpful and not too many classes, because then you just create too much abstraction and make it more difficult for yourself. So the idea would be you want the pipes, because you're going to be creating several of them and they're going to be moving and animating. You want a background, so that way you can put a mask on it for collision, and you want the bird. And that's all you want for your classes for the start. So that's what we're going to do first. We're going to import Pygame, Neat, Time, OS, and then random to generate the pipes. You have to initialize font in Pygame for some reason, which is kind of an annoying step, because if you forget it, it'll just crash everything every single time. But you start with some constants, just the width and the height, and what speed you want your pipes and your ground to be moving. And then these images are going to be required to animate it. I'll link those at the bottom of the YouTube video, so that way you can go to the GitHub and go ahead and download those. And I decided Comic Sans was going to be a good font for this, because it's kind of a silly video game. And then we just go ahead and start into our bird class. So we're going to want the constants for the array of images that we have, and then I'm setting a max rotation so that the bird will pitch up and down as it's jumping, to give it kind of a more dynamic feel to it, so it's not just a block floating through space. And then we want the speed it's going to rotate. And the animation time is actually how many frames between every time it flaps its wings. And we just initialize some standard values. So where it starts out is x and y coordinates. Start out with a tilt of 0, so it's flat right at the beginning. We're going to give it a tick count of 0. Tick count is going to determine how many frames have gone by, to determine how we're going to animate it. It's going to have a velocity of 0 for the start, because we don't want it falling or flying right at the beginning. And then just a height is just where we're setting it. So self.height is going to be instantiated and it's going to be assigned to its value. And the image count is which image it is, if it's 0, 1, or 2. And then we're instantiating it right at the beginning. So we're going to start out with a jump method, which is just having it lift in the air. And so this velocity is kind of just an arbitrary number that I came up with. It just matches with some of the physics that's later on. But it's negative because 0, 0 is the top left-hand corner of a Pygame window. So if you want it to go up, it has to go negative back towards 0. And once again, it's just the height being instantiated. And this, we're going to call move for every single one of our moving objects. So move is going to be called every single frame inside of our game loop. So it's only going to worry about a single iteration every single time because we're going to call it every single loop. And we're just going to increase the tick count, how many frames it's been. And then this might look familiar to some of you. It's just the kinematic equation for displacement. So it's just the distance formula to determine how far it should go up and how far it should go down given its velocity and just a generic assigned gravity. So then I have some fail-safes for if it's falling up too fast or it's going down too low. It kind of just looks sloppy because this is a game. True physics really shouldn't apply to it. It should feel a little bit more like a game rather than real life. So there's just some fail-safes for if it's falling too fast, just set it to a terminal velocity so it just falls consistently. And then it's the same thing for a jump. The transition and jump can be very, very abrupt if you don't have something smoothing it like this. So basically, if it's jumping, just have it jump a little bit more to keep it from jumping just a little bit and immediately falling back down again. And then this is just a large mess for how to actually tilt it. So essentially, if it's going up, you want it to tilt up. If it's going down, you want it to tilt down, but you have to check cases. You don't want it tilting up past its max rotation upwards, because if it's jumping, you don't want it to face directly up. A bird can't fly like that. And if you're going down, you want it to face directly into the ground for your 90 degrees. So it looks like it's in free fall. And the next one is just...
Hey Trevor, could you zoom in like just one a little bit, make it a little bit easier to see?
Is that better?
Yeah, thanks. Yep.
Okay. Next one is just a drawing window. We're going to create a draw for each one of our classes, and it's just going to be put onto the window that we create for Pygame. And so that's what this window is. And this, it just increases the image count like I was talking about before for which image it should be displayed. And this is the animation. It can definitely be more streamlined than what I have written here, but this works effectively. So essentially what this is saying is if the image count is less than the animation time that you have set before, so I have 5 set, so every 5 game ticks, it'll change. It'll be the first image. Once you hit twice the animation time, it'll now move on to the second image. And then after 3 times, it'll go to the third. 4, it'll go back to the second. So it'll flap up, and then it'll flap back to the middle, and then flap down again to have a more consistent motion. And then once it's reached this 5 times, it'll reset back to the original image with its wings down. So it'll restart the animation time. So that way it gives it kind of a seamless animation. And we also don't want the wings flapping while it's in free fall, because that kind of looks ridiculous to have your wings flapping while all you're doing is falling. So this just says if it's tilted down more than 80 degrees, it's considered free fall. So we just set it to be the first or the second image with its wings in a neutral position and just have it fall. And then this is just a fail-safe to keep it from animating, so that way when it starts again, it doesn't look sloppy when it animates again. It just starts it back at a point that's more consistent. This is one of the more complicated Pygame expressions that we have so far. So this will rotate the image as it's falling and going up. So transform rotate, you put in the image and you put in what degrees we have that sort of tilt. But what that does is it actually starts at the top left-hand corner of the image and it rotates that. So if it rotates like that, it looks strange. It looks like the bird is moving backwards while it's falling. So what we do is we create a new rectangle, and what we do is there's this Rotateimage.GetRectangle, and essentially what this does is it moves the center from the top left to the actual true center of it. So the idea is if it's already at the top left, you can find where the top left is supposed to be, and then you recenter it. And essentially what it does is it confuses Pygame into thinking instead of your shape being where it is, it makes it think it's slid down a little bit, so that way your center is now truly on your center. And then what it does is it blits it to the screen. So blit is just drawing. I think it stands for built-in, but... And then what we do is we create a mask for it. So Pygame has something called a mask, and I'll explain that a little bit more in a little bit when we get on to the pipes and the actual collisions. But that's the entirety of the bird class. Your bird is done, so we can move on to the pipes. Does anyone have any questions about the birds before we move on? Alright, so in pipe, we create a variable called gap, so that's just going to be the space in between the pipes that we have. And we use the velocity that we created above for the pipe in the base, so that way it's consistently moving at the same speed. And then we go ahead and initialize it. We don't need to worry about height, because that's going to be assigned later with our random. What we need to worry about is just default setting the X, so where we want it to appear. So you want it to appear just off screen, which is why we care about where the X is, but we don't care about the Y because that's going to be determined automatically for us. And then we need to keep track of where the pipe is and its images. So we start by setting top and bottom just equal to 0 to start with, just to have them instantiated. And then we need to transform the single image. We need to rotate it upside down, because what we have right now is just this bottom image of a pipe. So we need to rotate it and set it to be the top image of the pipe as well. So we just store that so we can move on, and then we set a variable called passed that'll determine whether or not a bird has passed that pipe yet. And then the set height method will start right next. And so what it does is it'll create the height based on a random range. I set 50 to 450, which is kind of a good default range. You can make it higher, you can make it lower, but then it becomes too close to the ground and too close to the top of the screen. And the distance between can be sometimes impossible for the bird to get under the first one and over the second one. So it's just an arbitrary value again. And then for the top height, what we want to go ahead and do is take the height of the first pipe, and we want to go ahead and subtract it by the height of the image itself, so that way the top left of the new pipe will be all the way above and off screen, so that way it'll come down to be the right height through. And then we want the bottom one to be the height assigned, and then we want to add, for it to move down, the gap that we have set, so that way you have an appropriate gap between the two of them. And then the move method is very easy. All you have to do is say when move is called, you translate it slightly based on the velocity that you have set, and then we just draw it to the screen using the same blit method that we used before, a lot less complicated because we already have everything assigned. So you just plug in the values and it just appears on screen. And then the collide method is a little bit more complicated. So we already have a get mask method set up for our bird. So what we want to do is create a mask for our top and bottom pipes, and go ahead and create an offset, which will be the distance between the bird's mask and the mask that surrounds the pipe. So what a mask is essentially, you have a bird. I'm drawing with my mouse, so just bear in mind it's not going to be pretty. But the hitbox around it is a true box, because you have the image is just an image file stored with dimensions. So what a mask does is it finds the actual pixels on your PNG, because we do not have a background. We can find the pixels and create a list or an array of just what's on it. So the collision, if you have two boxes and the boxes are in contact, but the objects themselves are nowhere near in contact, if you don't have a mask on that, it'll tell you that those objects have collided. With a mask, the objects have to physically collide, so it gives you a lot better collision, especially in a game like Flappy Bird where you're always rotating. One of those sharp corners could pitch up and just nick it and make it impossible to fit through the tube. So if you add a mask, it just makes it a lot more simple for it to actually work properly. And then these are points of collision between the bird and either the top pipe or the bottom pipe. So if this overlap function does not return anything, this will return none. So you can just check if these have a value, that means they've collided, so you just return true. So you can deal with that however you want to. Or if it doesn't collide, you just return false and there's been no collision and you're good to go. Do we have any questions about pipes?
I have a question with the masks. So does that automatically get set up with Pygame, or do you have to define the object?
So that's what this is. So you type in, it's Pygame mask is a function, and then you type in it's from surface, and it'll take the image that you have put in, and it'll delete all of the background. So that it's a PNG, so there is no true background on it. So the only pixels that are filled in are the ones that you want to worry about. So that is taken care of for you with Pygame. You don't have to worry about creating that. You just have to make sure you instantiate it. Alright, we're going to move on to base now. So you use the same velocity that you use for the pipe, so that way it looks like they're moving seamlessly together. And then the width is just the width of this base image that we have set up earlier, and then we need to instantiate image to be the base image. And then the only thing you care about is setting where your Y is, because your X's will automatically be determined for you. So we needed 2 X's actually for this to make sure it's moving seamlessly, because it is exactly as wide as the screen is. So this move method becomes a little bit more complicated. So we have 2 locations for it, and we've got this where we go ahead and set up. Does anyone want to give a guess about how I actually make the base look like it's moving properly? Where if your screen is exactly as wide as this screen, if the base is moving, it's halfway off the screen. So how do I populate the other half of the screen?
You just make a second base and then add
exactly. So you just start with 2 bases. One starts directly on the screen, one starts next to the screen, and they just slide across, and as soon as it gets to the edge, it just goes back to the beginning again. And that's what these methods do. It's what these if statements do. They just check to make sure, and then once it's off the screen, it just goes ahead and sets it back. And then it's just a simple draw method. We already have the location set up and the movement set up before it. And this is what physically draws all of these objects. So it'll call blit to create the window, and then what it'll do is it'll go through and it'll take each and every one of the draw methods that we created for each of them and populate them. So we have for all the pipes, well, we start with the background, and then we have for all the pipes, and then we render the text and draw it to screen, and then we draw the base, and then we draw the birds, and then we go ahead and update the display. So this main method is where we implement the neat. So for neat, it's a pretty basic implementation, which is why it's a good starter. So you basically need your input neurons, you need your output neurons, you need an activation function, you need to set your population size, have a fitness function, and then set your max generations. So that's basically the standard what to do to implement a neat function. There are a lot of different settings on top of that we'll cover in a little bit, but essentially for this, it is one of the easiest things that I could come up with that I could easily do it, which is why it was a good first step for me, and which is why it would be a good first step for you. So all you need is 3 inputs. You need your bird's height, its Y position, you need a top pipe location, and you need the bottom pipe location. But you don't actually need both locations of the pipes, because the neural network should be able to figure out where the top pipe is based on the bottom, or vice versa. So that would actually be a good thing for you guys to work on is get it to work with only one pipe as an input. I haven't had time to do that yet because I've worked on other things on top of it, but the output is very simple. Should you jump or should you not jump? That's all the outputs are. So for this, my activation function, I chose to use tan h. It's a pretty good function for something like this, and what it is just a hyperbolic tangent function. So that's what this is. What it does is it takes the values and squishes them towards 1 or -1, and it's exactly what we want. So it's, do you jump or do you not jump? So for this, I use 0.5 as my threshold. You can make it lower, but they just kind of jump too sporadically. There's not really a necessity for them to jump, so they just jump too much. So 0.5 is kind of a good standard place to start. And population size, for something this simple, it can almost guess properly. If you set it to be like 100, probably 1 out of 3 times, one of the initial networks that it sets up will automatically just be perfect and be able to complete it 100% of the time. So a smaller thing allows it to grow and actually learn from mistakes, so it's a lot better to visualize. And then the fitness function is the most important part of the entirety of using neat. It basically determines which bird performed the best. And so that's not just a function that you can plug in, that's something you have to implement in your physical code, and we'll see that when I go back and show the main method. So the max generations, once you've hit a certain number of generations, you either have a model that you want to save and use, or you need to go back and rework your fitness function because it still doesn't work. 30 is just a nice round number to use for this, just because if you get to 30 generations, you probably have a perfect thing, or you have terrible and it hasn't gotten past the first pipe. So what neat actually does is if you start with these 3 neurons that are your inputs, you have this one output neuron that you have set already. So what neat does is it'll set weights to each of these assignments to determine which ones are more significant than others, and what it'll actually do is create additional neurons they could be any number of things that it has access to. So it only has access to these 3 inputs. It can't know distance to anything else because there's no way for it to figure it out, but it can create additional steps for additional algorithms to get from here to here, and then one more step to get here. So it'll create and delete those based on what you tell it in a file. So that file is this. So I'll cover a couple of these, but the general gist of this is read the documentation for all of this, because even if I told you all of these, there's no way you would remember half of them. Some of them are very easily labeled, like all these neat functions. Your fitness criterion is max, min, or mean. So do you want the best, do you want the worst, or do you want the average for your fitness function? So it really depends on how you set it up. For some things, you're looking for a very specific value, so you might want the most average of them are the best. Or you might want the ones who receive the least amount of points to be the ones that you build off of. And then the fitness threshold is at what level of fitness do you determine this is as good as it's going to get. You don't worry about it. For this, I actually didn't use this value at all. I didn't call it, so we never actually reach 100. So we don't worry about that. This is where you physically set your population size. So if you change this, it'll propagate different populations when you run it. And then reset on extinction, that's extinction of a specific species. So a species is determined by the network that it's created. So each genome can have a different set of networks, or multiple genomes can have the exact same network. So if they all have the same network, that's one species. If they have a different network, that's multiple species. So there's really no point in completely starting over on a species extinction for something as simple as this, because it could just be the network was correct, it was one of the values inside of it that wasn't correct, so it says jump on this value of y instead of this other value of y. So if it runs into the pipe and dies, it has to completely find that network again for it to work. And then these are the activations. So what you can initially do with this is we have tanh functions determining this. So what you can do is when neat creates these additional neurons, you can have neat decide its own activation function. For maybe it wants to use sigmoid instead of tanh. You can set it to be allowed to do that, to create more and more complicated things. It'll take longer to train, but if you have something more complicated, it'll be a lot more accurate at the end. I went ahead and just set the mutation rate to 0 for both of these because it doesn't need to mutate. Tanh is basically exactly what it wants for this specific example. And then these are biases. I pretty much set these to be the default values because we want some bias in this so that way it can change and it's more biased towards the ones that get further. But we don't want 100% bias towards that because there's always the chance that it just got lucky and picked a random value and made it through the first pipe, whereas a better function just happened to hit it. And if we propagate on that specific one, well, it could have just been lucky and you could overfit to that one specific model and you'll never be able to find your solution. And a lot of these are important but not necessarily important to our example, so I'm going to skip them. And this one is it's hidden networks. So if you don't want neat to be able to touch one of your neurons, you want it to just be set for exactly what it is, then you can hide one. But for us, we just have 3 standard inputs and 1 standard output. And for the rest of these, I don't think it's important because we don't need to worry about stagnation. Stagnation is essentially if you don't make a significant amount of progress after this amount of generations, then you just kill it because you're not learning anything. You need to relook at your model. We don't need to worry about that because we have that taken care of in other methods. So that's something we don't need to worry about for now. But all that in mind, we're going to get into the main method. So we start by creating a list of networks and a list of genomes for our list of birds. So I use lists for these so that way the index it'll be the same for each of the 3. So bird 4 will have network 4 and genome 4 associated with it. So the network is the physical neurons that I was showing you in the diagrams earlier. A genome is essentially just each of the bird. So the bird is a genome. You have to pass the genome class into neat for it to understand what it's doing. You can't just pass a bird in because it has no idea what that class is. So you associate a bird with the genome. So first you just create them. So you just iterate through the genomes that you create based on how many you create with your feed forward file, this text file. It goes ahead and propagates this for you. And what it does is it just assigns a network to that and assigns a bird so they're all in the same index. Then we go ahead and create it. We set our base, we set our pipes, we go ahead and create our window. We use the clock so we can set a finite tick count, because if you don't do that, so a faster computer will have substantially faster tick times than a slower computer. So you can change this and get rid of this, and then you won't be able to actually visualize it if you have a fast computer. And animations wouldn't work properly, and that's kind of the whole reason why I animated it, so it would look prettier to show. And so we just start our game loop. We first assign run to equal true, so we can just run and then turn it to false whenever we want to kill it. And then we set, this is how many cycles we want to have in a second. So if you set it to 30, it's like a 30 refresh rate in a video game. And then this is just an event listener for if you hit the X, it'll go ahead and kill all of it. It won't just exit. It'll go ahead and stop the loop. It'll quit Pygame, and it'll quit out of everything that's currently running. So that way you don't have to worry about anything. It'll just automatically quit. It won't try and go back through the loop and stop. And so this is a pipe index. So it's which pipe we should be checking. So at any given time, there could be 1 or 2 pipes on the screen. We need to know which pipe that we should be looking at for our fitness function. So essentially what it does if there are birds on the screen, and if the lengths of pipes, so if there's more than one pipe, and the first bird has not passed the pipe, if the first bird has passed the pipe, actually, sorry, then we worry about the second pipe in the list. So that essentially means, for this, there's only one pipe on screen, so this is pipe 1. But say there's a second pipe that's here, so the bird has passed that pipe already, so we don't want our game looking at that pipe to determine score, otherwise it'll just infinitely count more and more score on top of it because it's already passed it. So it'll keep being successful in whether or not it passed. We want it to start looking at this pipe. And then because we had to check if there are any birds left, this is a great way to go ahead and break this loop and to create a new generation. So if there are no birds left, it'll break, it'll create a new generation, and it'll start the loop over again. And so this is how we're going to move our birds. So we call x and bird and enumerate birds, so that way we have the position in the index on x, and then we have the bird inside of the list of birds on bird. So we can move each and every bird, and then if it's made it to this frame, we go ahead and increase its fitness just a little bit, because this is going to be called 30 times in a second. We don't want to give it too much, but if it hasn't died yet, its fitness should be higher than a bird who has died. And then this is where we physically call our activation function. So we call it on the specific network that we're using. We call the activate function, which is a neat function, and then we go ahead and pass in our inputs. So these are our 3 inputs that we talked about earlier, and you go ahead and you get an output. And so if this first output is greater than 0.5, then you go ahead and jump like we talked about earlier. So the reason why this comes out in a list is because it's also formatted, if you have several output neurons, they're formatted in the order that you put them in. So we want the first one because it's the first and only one that we have. And then we go ahead and have our pipe handling here. So the idea is, should we add a pipe, we start it with false. We have a remove array, and then for each of the pipes, we go ahead and look through each of the birds to determine if the bird has collided with the pipe. And if the bird has collided with the pipe, we go ahead and lower its fitness just enough so that if you have 2 birds and one collides with the pipe and one makes it through the pipe at any given point, the one who hit the pipe should have a lower fitness than the one that made it through the pipe, so that way it doesn't prioritize just ramming into the pipe. And then if it hits the pipe, you go ahead and remove it from the list of birds. You remove its network and you remove its genome, so that way you don't touch those anymore. Those already have been stored away. You don't want to touch those anymore, so you just get rid of them. And then if a bird passes a pipe, you go ahead and change pipe passed to true, so that way you can add a pipe. And then it'll just go through, and when it comes back up, it'll just add another pipe randomly to the front so that it'll slide again. So every time it passes a pipe, it creates a new pipe. And then this just, once the pipe is off screen, it adds it to the remove list. And then when you add a pipe, you go ahead and you increment score. So every new pipe that's propagated, you get a new score, because every pipe is created when you pass a pipe. So it happens simultaneously, so whenever you pass a pipe, you get score. And then you go ahead and iterate through the genomes, and because it's passed the pipe, we go ahead and give it 5 fitness. So you've successfully made it through the pipe, you get rewarded, you get more fitness. Then you go ahead and add another pipe, and then we iterate and remove all the pipes that have already passed through. So that way we're not constantly increasing a huge array and just have a huge stack on our hands. And then this is for the cases where if the bird falls and hits the ground, or the bird tries to go up above the screen, because if you don't have this for above the screen, what the birds will actually learn they can do is if they fly high enough, they'll be above the pipe, so they'll never be hit, so they can infinitely just go forever. So if it flies above or it hits the ground, you go ahead and remove it just like you did earlier, and then we go ahead and move the base, and we draw the window again. So this is how we call neat. So we'll start here. So this is a function that neat recommends that you put in, so that way it can find your config feedforward file. So the idea is you just need to have it give it access to this directory, so that way you can pass in the path for this run function. And so it'll call this anytime you call a main function with the way we have this declared here. So whenever main is instantiated, it'll go through and it'll call this first. And run will first set the configuration. So it's neat.config.config, and this will be the default genome, default reproduction, the default, all of this stuff is what we have set here. That's each of these headers, and you don't have to call neat because neat is required. The rest of these are not necessarily required. If you don't touch them at all, it'll be default values, but it'll call each of these there. And so then we go ahead and we create our population using the population call that we had set. The reporter and the statistics are just a convenient little terminal display at the bottom, so that way you can see on the console like what's going on. It'll give you actual like statistics for it. So what is your fitness? How many made it this far? What is your average fitness? What is your average mutation on certain characteristics? And then so this, you can save this winner as who has made it this criteria. So this is how many generations you want to go through, and then it'll save whatever your genome and whatever your network is onto this winner, so that way you can save it and use it again in the future. And so this is what you have for your fitness function. So for me, I just called it main. It's just because main is the function that we're calling it. If you had a more complicated thing and this was just a small part, you might call it like get config, get best. You could call it whatever you wanted, but it's just convenient for mine to be main. So once you put all of this together, you have a Flappy Bird game, and it'll slowly learn. And because of the simplicity of it, sometimes it'll take 2 generations, sometimes it'll take like 10. It all depends on how it can mutate those networks to create a successful game. But now that they've passed about 5, these birds will go on forever. They will never die. All right, do we have any questions?
How long?
Could you explain like genome and population again?
So a genome is essentially a unit in the population. The population is how many for each generation you want. So if you have a population of 1 and you have a population of 100, that's how many genomes will be created for each generation. And a genome it's essentially assigning a certain thing a value. So if we have an array of 25 birds, you need 25 genomes to be associated, so that way neat can actually use them properly. So genomes have a certain number of attributes associated with them that neat uses to give them their own characteristics. So a genome is not important in solving like how this works. That's what the network is for. But a genome assigns a certain class to a certain network. So it's an intermediary step between your bird and your neural network. It's what ties them together.
Okay, that makes sense. Thank you.
Did you have a question, Jonathan?
Yeah. How long did this take you to make?
This took me probably only about like 20 hours. I worked on a couple hours a day for about a week.
I guess if there's no more questions, you could show people your fancy drawing thing if you want.
My fancy drawing thing.
Yeah, the dog thing.
I actually had a question real quick.
Oh,
Go for it.
Would you go over how you made it so the neural network didn't just like preference the birds that weren't just randomly jumping, like that there was a clear strategy here and wasn't just pure luck at the bird? Was that something you did, or was that just the neural network finding a way?
okay. So for that, it's a number of things. It's this bias. You set the bias to be 30 and negative 30, so it kind of squashes it between two values. As far as I know, these are just arbitrary values, but I used examples that I could find to say this is a large bias, this is a small bias. So this one is a very small bias, and it's also actually it's probably easier just to find it here. So in the tanh function, so we call anytime it's, let me see where if I can find it. Maybe down here. Okay. So when the output is greater than 0.5, then you determine a jump. Because otherwise it's seemingly random, these values that are right around 0. Once you get to a more significant value, it makes more sense to jump. Because statistically, being higher than 0.5, you have a lower error in whether or not you should jump. Right at this median, it doesn't matter if it's 0.00001 or negative 0.0001. It's the exact same thing, so there's really no point in determining jump or not jump.
Okay.
I had a question about NEAT. Could you highlight some of the main differences or like the enhancements between a regular genetic algorithm and NEAT?
So NEAT is essentially just a regular genetic algorithm, but it does a lot of the legwork for you, the same way that like you would use sklearn when you're using like a standard neural network, where it takes care of some of the steps for you, where all you have to do is set the number of layers and neurons inside each layer, determine what you want to do, and then how many times you want to train it. It's basically a tool just like that to help you get to your end goal easier, just like sklearn would be.
Oh, okay, got it. Thanks.
But if you were interested in all of the specific details, it's right here. I think Jonathan linked it in the chat a little bit ago.
Yeah, I saw. Yeah, so from a really simple genetic algorithm, it seems to have a lot more configurations than like a very basic one. But yeah, I'll take a look at those settings. I think since it's a package library, just like sklearn and other things, it seems to have a lot more details.
Right.
Anyone else have any questions? Yeah, I think if you wanted to, we have 10 more minutes. Show everyone your fancy dog.
Fancy dog it is. So the idea behind this is that you can create an image. So you have your context image, which is going to be the image that you have for the base, and then you have your style image for what you want the context image to look like. And so when you run this, it'll go ahead and train at the bottom. But essentially it'll paint the context image in the style of your style image. So I saw a video that NVIDIA did where they did this kind of thing, but what they did was it worked in real time. So what they could do is they played the entirety of like How to Train Your Dragon, and as it was playing, they changed the artist interpretation of it. So they changed it from Monet, and then they changed it to Kandinsky, and they changed it to all these different famous painters, and they were able to do it seamlessly in the middle of a live streamed movie. And when I saw that, I thought that was really cool, and I could do something like a simpler version of it just on an image pretty easily. So this is about done training. And so these are just like, they're Sobel edges, and these are gradients for each of the directions. I use those just for my own sake, so that way I can create this final image based on these two input images. So if I change the style image to be a Kandinsky, what it'll do is it'll go ahead and paint it that way instead of this way. So if I go and take the relative path, all I gotta do is paste it in there and then retrain it. Okay, it's refusing to train right now. It looks like it hasn't terminated the last process. Okay, so if I kill it, and then run it again, it'll paint it in Kandinsky this time.
How does this one work? Like, what are you comparing it to? So, like, for the Flappy Bird one, you had an output which was the score, and the higher the score, the better it is.
Right.
What are you comparing it to in this case?
So this is a completely different type of learning. The other one is more of like a cue learning kind of style. And so what the cue learning kind of style does is, based on these inputs, it will train itself based on if it did well or if it did poorly. So there is a TensorFlow. It's called TensorFlow Hub, which has like a bunch of data sets housed inside of it. So I use those data sets to train, and I go ahead and format the data inside of it. There's a lot of data formatting in it, which is the extent of why it's most of it. But most of the actual training is very, very simple inside of like a singular class. It's towards the bottom. But basically, this right here is the entirety of the training and then printing, whereas all of this up here is just formatting the data properly. So that's what TensorFlow Hub is really good for. TensorFlow Hub has a huge collection of all these data sets, the same way like Kaggle has a lot of data sets, and then all you have to do is format the data properly, determine what parts that we want to use, and then you just format it properly, you call them, you assign proper weights on them, and you just use Keras to kind of split everything apart for you. You set up your neural network, and then it trains. So it's a very different style of machine learning. I actually don't remember specifically what model I used for this one. But I know I used the atom activation function. That kind of answer your question, or?
Yeah. A lot of those things like went over my head, but I would have to like look up some things because I didn't understand a lot of it.
Like a very low level understanding of it is like cue learning, like the Flappy Bird, is if you do well, you get rewarded. Whereas something like this is you use data sets with a lot of images and a lot of context images, and you kind of train against what already exists. So that way you can use kind of this edge detection and Sobel filter kind of detection to just take essentially the brush strokes of your style image and just throw them onto your context image. So one you're training before you do it, the other one you're training while you're doing it.
Oh, okay. I get that. Thank you.
Yep. Does anyone else have any questions?
What fun stuff are you working on now with machine learning? Anything new and exciting?
I actually don't have a specific project set up because I'm waiting on research.
Do you know enough about it to like give us all a synopsis, or is it not to that point yet?
It's not at that point yet.
Okay. Once you do something exciting, we'll bring you back again. You can talk about research.
All right, sounds good.
Trevor,
Yeah,
where are
thanks.
you working?
So I'm currently talking to people at McFarland to work in population health. So I've talked to the people who are in charge of it. The only thing I need to do now is speak with the head of HR to get onboarded to get my HIPAA registration and all that kind of things.
Cool.
But yeah, thanks Trevor for giving us this talk about fun machine learning Flappy Bird stuff. Thanks everyone for coming. It's always great to have you at these meetings. We have a meeting next week same time with Sean Van Wilden, who is Iowa State grad working in the Silicon Valley. Should all definitely come back and check out that talk. But yeah, thanks everyone for coming. This was great.